So you have two containers. Each one has 1 mole of an ideal monatomic gas. The atoms in container X have more Ke than the atoms in container Y. That means that temperature of X is more than temperature of Y. The containers are thermally insulated. That means there's no heat going in or going out. But they're going to be in contact with each other. So what's going to happen is that the collisions between the two containers will be able to transfer the energy from container X until they become the same temperature at some point. Okay? So finally, the temperature of X is equal temperature of Y. But the heat should leave because of collisions. Container X and must go to container Y. So the answer is going to be A. Okay. So a sound source emits sound of a single frequency in all directions. At the instant shown in the figure, observers A, B, and C are at the locations shown and are moving toward the sound source with the speeds indicated. So they will all hear higher frequency than normal because they're all going toward the source, correct? But the one that's moving with the higher speed will end up hearing the highest frequency, meaning that f of b has to be the highest. And the ones that are moving with the same velocity will have the same frequency heard. So f of a is equal to f of c. So the answer is going to be choice D. Question 3. When monochromatic light of frequency f is incident on a metal with intensity I electrons are rejected with maximum K, what change would cause the electrons to be ejected with the maximum Ke more than before? So look, the equation says Ke or K is equal to HF minus the work function. So in order to increase the K, you must increase the F. Okay? So you must increase the F. There is nothing around that. So it's not B, and it's not C, and it's not D, and it's I. Okay. Good. So, question 4. A circular loop of wire with a radius of 5 is placed on a uniform magnetic field of magnitude of 2 millitesla. So right now we know that B is equal to 2 times 10 to the power of negative 3 Tesla. And the radius is equal to 0.05 meter. The angle is equal to 60 from the y-axis. What's the magnetic flux in the loop? Let's bring up the equation sheet. Okay, so here's the equation. B is 2 times 10 to the power of negative 3 cosine of 60 degrees. Make sure your calculator is in degrees. And area is the area of, if there is a radius, we're talking about a circle. So pi r squared. Let's do the math. And I got choice A. Okay. Question 5. Process Z to X is isothermal. So what does isothermal mean? That the temperature of Z is the same as the temperature of X. Okay. Now, what they want is the force on the piston during X to Y. Now we know that pressure is equal to force over the area. So force is equal to the pressure times the area. And the pressure from X to Y is what? Is P1. So P1 times the area. So the answer is going to be choice C. During which process, if any, is the amount of the work done on the gas same as the amount of energy that the gas exchanges with the surroundings? Okay, what they're saying basically is delta U is equal to Q plus W. So that means they want the delta U to be 0, which would make the Q is equal to minus W. Okay. And so at which point in the graph is delta U 0? We were told in the question it's point Z to X, because isothermal. So here delta U is equal to 0 from Z to X. 7. At which labeled point is the magnitude of the electric field the greatest? Well, electric field has to be leaving the most positive area and going to the most negative area, right? But so look, we know that the E is equal to change in V over the change in the R. This equation is actually in your equation sheet. And so E seems to be, let's see, if we do 4 minus 2 for B, we get 2 volts. And if we do 0 minus negative 2 for A, we also get 2 volts. And if we do that for point C, we also get 2 volts. And if we do that for point D, saying minus 2 minus negative 4 will equal to also 2 volts, right? So they all have 2 volts between the two lines. That's not going to matter. What matters is just the distance. Whichever has the least distance between the lines will have the most E. So which lines are closest? At what point are the lines closest to each other? At point A. They're only this much compared to this much, and that much, and that much. So A has the least distance, it must have the greatest electric field. Okay. Students collect data to determine the focal length of a converging mirror, which looks like this. They place the object at various distances from the mirror and then move the screen until they see a focused image of the object on the screen. Right. What's the approximate focal length? So 1 over F is equal to 1 over SI plus 1 over SO. Okay. Choose any point on the graph that is accurate. So like, don't choose this one. That's not very accurate reading.
2020.
Exactly. 2020 is going to be the best reading. So the SO is 20 and the SI is also 20. Okay? They're both 20. So 1 over F is 1 over 20 plus 1 over 20, which is 1 over 10. Flip and you get 10. F is equal to 10 centimeters, and so the answer is going to be choice A. Okay, a student has 3 sunglass lenses. Lenses A and B have identical polarization patterns. When unpolarized light passes through lenses A and B, it becomes polarized. Okay, polarized means only passing through one direction. Which of the following arrangements of lenses would have the most light blocked? For the most light to be blocked, okay, they have to be, the polarizers, they have to be perpendicular to each other, right? Now, right now, lens C is not a polarizer. Why? It doesn't have any lines. So it lets all the light through. But B and A will be polarizers because they can block some part of the light. Now right now, if you just put A and B parallel to each other, you will have a lot of light going through because they're parallel to each other. They must be instead perpendicular to each other. So B. Let me explain to you why. So look, this is lens A. And so this is light coming in through all the directions. It's unpolarized yet. And this lens A lets only the parallel portion goes through. And now it will face lens B, which is like this, which only allows perpendicular portions. So now there is no light going through lens B. Okay, 10. Cylindrical resistors 1 and 2 are made from the same material. Resistor 1 has length of L, diameter D, and resistance R1. Resistor 2 has length of 2L, diameter 4D, and resistance of R2. Look, let's just talk about the resistance equation. So R is equal to resistivity times length over the area, which is just pi R squared. Now, what's R? R is basically diameter over 2. So R squared means diameter squared over 4. So replace the R squared with D squared over 4. Right now, if I rearrange the equation, it's going to be R is equal to resistivity times L over pi D squared over 4. Essentially, R is going to be direct with the resistivity, direct with the length, but inverse with the D squared. So, let's see. So, R2 is equal to, what's the resistivity of R2? They don't talk about it, right? So, we're going to remove that from the math. But the length is going to be how much for R2? 2L. And D will be 4. You will square it. So 4D squared. So 2L over 16D squared. That's for R2. How about for R1? The length is L. And diameter is just a D. You square it. Okay. So now we're going to say R2 over R1. So 2L over 16D squared over L over D squared. Do some math. 2 over 16D squared times D squared over L. Cancel these squares, cancel the L's. What do you get? 2 over 16, which is 1 over 8. Yeah. So here we have a converging lens because it's, we're told, and it's also because thick in the middle. Okay, the object is placed at distance of 2f. So as of now, SO is equal to 2f. And now, of course, lenses are known for refracting. Light has to bend as it goes through the lens. Okay. Now, if the distance of the object is more than f, you will get a real image that appears on the other side of the lens. So the image has to appear on the right side because the object is on the left side. And in A, they show us that the image is appearing at F, which means the left. But it should appear on the right side. So it's not A.
And it's not B.
And it's not B. It's either going to be C or D. Okay? So, how do we know which one? You actually have to know the cases of the
It
lens.
should go through the F.
It should go through the F. Let me show you the cases. So this is the case that I'm talking about right now. When the object is placed at 2F, when the SO is equal to 2F, the image will form at 2F, but the light ray has to go through F. Okay, so look, when the SO is equal to 2F, the SI is also equal to 2F, but the light rays, one of the light rays at least, a light ray must go through F. So the answer is going to be choice D. Okay, 12. Each of the following pairs of graphs represents the change in air pressure due to sound waves as a function of time. at a single location. What you want is a beat frequency of 2. That means when you do the frequency of the first wave minus the frequency of the second wave, in the absolute value, you get 2. That's what it means. Okay. So look, let's see what makes a wave, or how many waves we have. That's called frequency. So here we have a wave. This whole thing right now in red is a wave. Okay, so you must have a full trough and you must have 2 combined half crests. So right now here the frequency is 1. Okay, here we have one wave, that's f of 1. Then we're going to have the second wave and a bit of the third wave. So here the f is maybe, let's say, 2.25. Okay, so if you minus them, you get 1.25, not 2. So it's not going to be choice A. Let's look at choice B. So here we have, that is half a crest, a full trough with half a crest. So right now here we have f of 1. Now here we have half a crest, a trough, half a crest. So far it's one wave. Here we have half a crest, a trough, half a crest. That's a second wave. We'll use the third color. Half a crest, a trough, and so half a crest and a trough and half a crest. Okay, so that would be so far and a bit of, and we're gonna actually have a bit more if we keep going. So anyways, here the f is like a 3.5. Right now if I minus them I get 2.5. Okay, let's see, here I have a crest, half a crest and half a trough. Here the f is 0.5. Here I have half a crest, a trough, and half a crest. Here f is actually a 1. If you minus them, you get 0.5.
So what is C?
Let's look at C. So that's half a crest, a trough, half a crest. That's f of 1. Half a crest, a trough, and half a crest. That's 2, and a bit of a third wave. So that's going to be f of 2.25. But here is going to be a crest, half a crest, a trough, and half a crest. That's f of 1. Then half a crest, a trough, and half a crest. That's 2. Half a crest, a trough, and half a crest. That's 3, and a bit of a third. That's like 3.5. If you minus them, you get 1.25. So none of them is fully accurate, but the closest one to 2 is which one? The 2.5. That's the closest one. Okay? So it's choice B. Okay. So they want here the net force exerted on the middle sphere by 2 other spheres. So the plus 5q is going to try to push it away, and the plus 2q is going to also try to push it away. That means you have to minus those 2 forces because they're going to go in the opposite directions. Let's start with the plus 5q force. So you're going to say F is equal to K Q1 Q2 over D squared. And the plus 2Q is going to be K Q1 Q2 over again d squared. This becomes 5q squared times k over d squared. This becomes 2q squared k over d squared. Now what do? We should now minus them. So it's like doing 5 minus 2, which is a 3. The answer is going to be choice B. Question 14. So the potential difference across the 1000 ohm is equal to 5 volts. Now the 1000 ohm and the R are in parallel. That means they must get the same voltage. So if this is 5 volt, that's also going to be 5 volt. Okay. So this is 25 volt. So because the parallel branches receive 5 volts, that means that the series branch received 20 volt. Because what you do is you do 25 minus 20, whatever remains has to go equally through the remaining branches, which is the 5 and a 5. Okay. Now some will say, no, wait a minute, 5 plus 5 is a 10. This guy must only go at 15. That's not true. That's for series me. But in parallel, if they both get 5, that means you just take it as a 1/5. So this guy here receives 20 volts. Let's see how much current that is. So V is equal to IR. So 20 is equal to I times 2000. I is equal to 0.01 ampere. Okay. So that's the current, 0.01. And we can also find out how much current goes here. And we can minus from the 0.01 to know how much current goes through the R. So V is equal to I times R. I is equal 5 over 1000. So 0.005 amp. So the 0.01 amp minus the 0.005 will give you how much? 0.005. So this guy here receives 0.005 amp, which means this guy receives the same amount, 5 amp. So now we're going to say V is equal to I R. R is equal to 1000 ohm. Okay, 15. Which of following correctly indicates the temperature of the black body and the rate at which it emits energy at the time of T2? Okay, so let's just see if there's an equation that's going to help us with this one. Let's go to the equation sheet. So this equation right here is going to matter to us. Lambda max is equal to B over T, and also power is equal to A sigma T to the power of 4. We need those two equations. Okay, let's see what's happening here. So basically, the wavelength got doubled from lambda to 2 lambda. And as we can see here, lambda max is equal to B over T, and B is just a constant. So that means when the lambda max doubles up, the T has to get halved. Now looking at the power is direct with the T to the power of 4. That means if the T gets halved, you put T as half, the power of 4, 1 over 16. So the power has to be 16th of the old one. And temperature has to be half of the old one. So it's choice A. Okay. Samples 1, 2, and 3 have different amounts of the same monatomic ideal gas. The samples are placed in different closed containers. And we're just going to be comparing their temperatures. So you should always look at the x-axis for this comparison, which is the speed, and which sample has the most speed. Actually, sample 3, because look at the peak.
Yeah, it's 3.
I mean, sorry, yeah, look at the shifting. It's all the way to the right side. So sample 3 must have the highest temperature, because more temperature means more speed. And sample 2 is in between, and sample 1 is the one that's least to the left. So T1 has to be the least. So it has to be choice D. Okay. 17. So we got a square loop with a side length of 0.6. Loop is in the region of the magnetic field, initially Bi, and then the field will decrease at a constant rate until it becomes a zero field at the time of 0.1. Induced EMF is 0.5. What's the amount of the Bi? Okay, so let's just invoke the equation of magnetic flux. Change in flux is equal to B times the change in the area, okay, times cosine, but there's no angle here, so we just leave it like this. And also, EMF is equal to change in flux over the time within the absolute value, okay? So, basically, B times change in the area over the time.
Oh, yeah, time.
Now, what's the area of a square? Side squared. So we can replace the delta, and here the side is just called, let's just call it L. So A is equal to L squared. So we're going to put here L squared. Okay. Now we know that the field becomes zero at some point. So essentially we're going to say EMF is equal to B L squared over the time. So B is equal to T times EMF over L squared. The time is given to us as how much? 0.1. EMF is given to us as 0.5. And the L is 0.6, and we square it. And let's see how much we get.
0.13.
Zero-
14.
So 0.14 after rounding. That's good. Question 18. Lenses 1, 2, and 3 are the same size and shape, but are made of different materials with different indices of refraction. So a small object, which is the thick arrow one, is on the left of each lens. Okay, you see how they're bending at different angles or at different places? That's because they have different ends. Right now we're seeking to find which one is the highest end. So, what's the equation to use here? Let's use Snell's law, right?
Yeah.
Which says N1, which is the air,
Yeah.
times sine of the incidence, sine of theta I, is equal to N of the lens times the angle of the refraction. Okay?
There aren't that many MCQs to practice on.
Okay. There are in the college board.
Yeah, but
Okay. So N
not like a full test.
So N air times sine of theta I is equal N lens times sine of theta R. And so we're going to say sine of theta R is equals over sine of theta I is equal to N air
Over N lens.
over N lens. Okay. Now, Which one has the most bending?
2.
2 has the most bending. Let's flip this equation here, because I want to have the sine theta I on top. So I'm going to have sine of theta I, which is just the sine of the theta in the air, over the sine of the lens is equal to n of the lens over the n of the air, which is just a 1. So essentially, the more the bending, the more the n. So when this is higher, the n is also higher. When the ratio of sine theta air to sine theta lens is higher, n lens is going to be the higher one. So the one's bending is going to be having the least sine theta lens, right? So the most bending is the least sine theta lens. And if sine theta lens is less, n lens will be higher. So lens 2 has the most bending, we can tell, right? That means n2 has to be the greatest. So it's not A and it's not C. Which one has the least bending? Has to be the
lowest n.
Yes. So the least bending is in lens 3, right? So n of 3 has to be the least. So I guess the rule is the more the bending, the more the n. N bends. So more bending means more n.
So it's B.
So it's choice B. Okay. Question 19. In scenario 1, students shine a beam of monochromatic light of frequency f on a pair of slits. Okay. So y1 is distance between the central band and the next bright band. But then you will take the whole thing and put it in a liquid. Okay. Whose n is more than 1. So what's going to happen to the thing, to the y? Let's just think about this way. There's this equation in your equation sheet. Let's just bring it up. It is, to be exact, this equation right here. D y max over L is equal to m lambda. So right now we're dealing with this equation, to be specific, and because there's nothing mentioned about, okay, actually wait, next bright band means m is equal to 1. So our equation just becomes d y max over L is equal to lambda. So essentially y max is equal to lambda L over d, right? And originally our y max is just a y1. Okay, so y max is equal to y1 inside of scenario 1. But now things are about to change, because now we're going to take the whole device and put it in water or fluid whose n is more than the air's n. Okay, so if the n is more, when light travels to a higher n, what happens to the speed of light? It becomes less. When the speed of light becomes less, the lambda also becomes less. Okay. So essentially now I can say n is equal to c over v, and v is equal to lambda f. So essentially lambda is equal to c over nf. Okay. So lambda is going to be inverse with the n. So It's like saying we will simply divide our y1 now by n. Because lambda is inverse with n, it's like saying we're going to be dividing our y1 by n. Essentially. Okay? Yeah, because why is that? Because look, y is direct with lambda. And lambda is inverse with 1 over n. That means y is going to be inverse with 1 over n. So A. Question 20. Two conducting plates of area A are separated by a distance d. Now, as we know, electric field always leaves the positive plate and goes toward the negative plate. So it's going to be traveling in the negative y-axis direction. Okay. So it's not A and it's not B. Okay. And
It's D.
that's D. Yeah, because the field always goes from positive plate to negative plate. 21. Let's invoke the equation to find the potential difference when you're given the field. E is equal to change in voltage over change in distance. Right now we're looking for the change in voltage, which is E times change in R. So 5 times that times distance is 0.80 millimeter, which means 0.8 times 10 to the power of negative 3. You must always make it to meters. We'll get 40. 40 volts. Okay. So look, here we have a nucleus of mass m is at rest when it emits a high frequency photon of frequency f. The photon moves off in a direction and the nucleus recoils with a speed in the opposite direction. So the photon goes this way and the nucleus goes the other way. So basically, the energy that's contained in a nucleus is equal to small m c squared, where small m is called the mass defect. So that means you must have a small m by itself times c squared, because that's the original energy. So it's not c and it's not d. Now, what's going to happen is that the original energy is equal to the kinetic energy of the remaining nucleus. And the nucleus mass was m, but now it decreased by delta m, v squared, plus the energy of the photon, which is hf. This is called the conservation of energy, basically. And so it's going to be choice A. 23. In which circuit is the total stored charge on the positive plate of the capacitor the greatest? Okay. So Q is equal to CV. Okay. And which circuit here has the most C? How do we find C when it's in series? It's the opposite of the R.
Yes.
You must do 1 over. But if you're doing them in parallel,
You just add them.
you just add them up. So which combined C's here is the best, is the highest, I mean?
The ones in parallel.
Exactly. So here our full C is going to be 3C. That's the highest C possible, and the Q is going to be direct with C because of the equation. And
C.
so C. I mean, yeah, choice C, which is circuit Z. Okay. So here we have a string of mass M and length L attached to one end of the pulse generator. The string hangs vertically with a block of mass 3m at the lower end, as shown. The pulse generator is used to send a wave through the string, which expression is equal to the speed of the wave at the midpoint of the string, a distance of L half below the pulse generator. So basically here, at this distance. Okay, let's look at the equation sheet. So we're going to actually have to look at this equation here. V string is equal to tension over mass per length. So look, what we know is that we are supposed to be combining things, because we have here the mass of the block, and here we have half the mass of the string. So this part here. So we're going to have half of mg. We know it's half the string because we were told at the midpoint of the string. That's why it's half. Plus 3 mg. So the force is equal to half mg plus 3 mg. Come here and replace the force with that. That's going to be 3.5 mg, or in terms of fractions, 7 over 2 mg. So we're going to have 7 over 2 mg over ml. Cancel the m's. So V is equal to 7 over 2 g over L. Or just 7 over 2 GL, basically. Wait a minute, sorry. Oh, that's M per L. M per L, so the M's will cancel. So you're going to have 1 over L, and if you do some simple math, it will, go back and become a numerator. So it's choice B. Okay, question 25. We have a small solid sphere X is made of an insulating material and has excess negative charge throughout the volume. So we have, insulator, so it's going to have the negative all out. And sphere is made of a conducting and has, in a conductor, the negative charge stays on the outside. Okay. So, I don't know, is that a mistake or something? I think they mean to put this guy here. Wait, let me just do something. I believe that's what they mean, if I'm not mistaken. So we're going to cancel these and just look. Now look, what you're going to do is you're going to bring the two spheres close to each other, right? And charges in an insulator, like this one, don't move. But charges in a conductor are able to move. So if the charges were spread out, were spread throughout the entire X, they must remain spread through the entire X. They must remain.
And the conductor will move.
So it's not going to be choice A because they're going to the edges.
Yeah.
It's not D.
It's not going to be D. It's going to be C.
Yes, because when negative C is negative in a conductor, they try to escape to the other side. Okay. So choice C. A student measures the incident angle theta I and the refracted angle theta R. Right. So look, if we do n I sine theta I is equal to n refraction sine theta refraction. Now, of course, ni is just a 1. It's air, so it's gone. So then we're going to just say that sine of theta I, wait, if this is the y, right, and this is the m, and this is the x, then the slope is equal to the incidence, the index of refraction of the, index of refraction of the second medium. And they want the slope to be n. So that means you will have sine theta I as the y-axis and sine theta r as the x-axis, which means you will plot sine theta I as a function of sine of theta r. So it's choice D. Okay, so a student is doing an experiment in which the monochromatic light passes through a double slit, creating a pattern of dark and bright lines on a nearby screen. The student has a red light and a green light. You want the greatest separation. Let's bring up the equation sheet. To be specific, we're going to be looking at this equation here. dy max over L is equal to m lambda. So that's our equation sheet. And right now, if I rearrange it, I will have y max is equal to m lambda L over d. So if I'm comparing red light to green light, which one is going to have more wavelength? You should know this.
I
Red.
do know, but I forgot all this info.
Okay. So you want to have the greatest separation. That means you must have more lambda, right?
Yeah.
So that means it should not be green, it should be red. And D means the slit separation. So Y is going to be direct with lambda and inverse with D.
So it's going to be small.
Yeah. So you want to make the lambda bigger, you want to make the D smaller, which is choice D. Great. So initially the charge was QO. We had a single capacitor. But now we're going to have a second capacitor, but of course the charge is conserved. So the QO has to be the same. Okay. So let's just see what's happening here. Q is equal to CV. Okay. And we can call this Q1. We can call this Q2. Okay. So Q is equal to CV. And so look, since the the CO over 3 is uncharged, it has to get all the charge from the CO.
Okay.
And whenever you put a charged object with an uncharged object, the charge is going to move from the charged to the uncharged until their voltages become the same.
Yeah.
So now essentially we can say that the V of 1, the V of the capacitor on the left, is equal to the V of the capacitor on the right. Now we know that Q is equal CV, so V is equal Q over C. So we're essentially saying that if V1 is equal to V2, we're saying that Q1 over the left capacitance is equal to Q2 over the capacitance on the right, which is CO over 3. Okay. Now, if I do some math, I will simply cancel the CO with the CO. So I'm going to have Q1 is equal to Q2 over 1 over 3, which means Q1 is equal to 3Q2, essentially. So Q1 is equal to 3Q2. Now, like we said, charge is conserved. So before, all the charge was on CO. So CO was equal to QO. But then after, the charges of the CO and the CO over 3 must be equal to now QO. So now we're going to have CO plus CO over 3, charge-wise, is equal to QO. Okay, so essentially, we could say Q1 plus Q2 is equal CO. The charge of capacitance 1 and the charge of capacitance 2 is equal to CO. Now, Q1 is what? 3Q2. So I'm going to replace Q1 with 3Q2. So 3Q2 plus Q2 is equal CO. So 4Q2 is equal to CO. And, I mean, sorry, I meant QO. So 4Q2 is equal to QO. So essentially Q2 is equal to QO over 4. So the charge on capacitor, the C over 3, must be equal to QO over 4.
C.
So choice C. Exactly.
This would take so long in the exam.
This will take so long in the exam.
Yeah.
Okay. Okay, maybe there's an easier way, which is that the more the capacitors, the more the charge, if the V is constant. So Q is equal CV. So given that V is constant, because there's no, because they must share the V, they must have equal V's, because the charged gives the uncharged, then Q is going to be direct with C. And so the higher the C, the higher the Q.
Yeah.
So because CO is 3 times CO over 3, right? So that means that the capacitance on the left is equal to 3 times the capacitance on the right. That means the charge of the left is equal to 3 times the charge of the right. And so that's why choice C makes sense, because 3 over 4 QO is 3 times Q over 4. So it's going to be choice C.
Yeah, that's easier.
Yeah. Okay. At 29, the student wants to increase the temperature of an ideal gas of an insulated cylinder that's insulated room temperature. Okay. Let's bring up the Khalid sheets here. So this information is actually going to be important. When the piston is pushed in or pulled out very quickly then the Q is equal to 0. Well, here it says you want to increase the temperature. That means that delta U has to be positive.
Yeah.
And delta U is equal to Q plus W. Let's look at choice A. If you were to push the piston very rapidly, that will make the Q 0.
Yeah, I know.
And if you push the piston, that means you're compressing the gas. So delta V is negative, so work is positive. And if work is positive, that would also make delta U positive, so temperature will increase. And look at what they say afterwards, because no energy is going to be transferred to the surroundings by cooling process. That means the Q is equal 0, which we know when they say very rapidly. So it's choice A. Question 30. A current carrying square loop of wire has side length of 2r and is in the plane of the page. The bottom side of the loop is positioned at a distance of r away from the long straight wire. The long straight wire carries a current of I directed to the right. Counterclockwise. Okay. You want the force magnitude.
Yeah, the B equals mu.
The equation says the force, the magnetic force made by a current carrying wire is going to be mu I. It's actually going to be ILB, and B is equal to mu I over 2 pi r. Over 2 pi r. Now, how long are we talking about? 2r. So replace the length with 2r. Okay. And now, look, this side and this side, they're equally distant from the wire, correct? And the current here will be going up and the current here will be going down. That means the forces will cancel on each other because they're equally distant from the wire and the currents go the opposite directions, I mean. Now, what we gotta do is worry about those two sides. Because the current goes in the opposite direction, but they have different distances from the wire. And so we're gonna have to minus the magnetic forces. Okay? So we should find the magnetic force on this one, find the force on this one, and then we should minus them. So we're going to say I, L, which we said the length of 2r is a square, mu I over 2 pi. How far is this face from the wire?
2R.
No, it's 2r plus the r.
So 3R.
So 3r. So 2 pi 3r. We can now cancel the r's and make the I times I squared. And also cancel the 2's. So you're going to have mu I squared over 3 pi. That's for the top wire. For the bottom wire is going to be I, the length is 2r, mu I over, how far is the bottom wire from the wire? I mean bottom segment from the wire? 1r, right? Just 1r. Now what do? We cancel the r's, we cancel the 2, we multiply the i's to become I squared. And now because the current goes in the opposite direction, you must simply now minus them with each other. So you should do this minus that. This is like saying 1 minus 1 over 3. It's like the same thing, right? Which is 2 over 3, which is choice B.
I kept saying Saturday and did not show up on Saturday.
So like, let's find the resistance of this branch.
Okay.
Which is 1 over r. Let's find the r parallel, basically. Okay. So r plus r would be 2r. 2r plus 2r. So 1 over 2r plus 1 over 2r. 2 over 2r. You must then flip and you get r.
Yes.
And now my method says EMF in the parallel is equal EMF minus EMF in the series R
over the circuit.
Over the circuit. So what is the R of the circuit? It's this one, the one in series, and the parallel combination, which is 2R. So EMF minus EMF, R series is going to be the R. That's the one in series over 2R for the R circuit. EMF minus half EMF which is EMF over 2. Now, that's how much voltage is received by each parallel branch. So that means the 2R, which is this one here, receives EMF over 2. And now they want the power. So now we're going to say power is equal to voltage squared over R. In our case, we're looking for the voltage in the 2R. So instead of R, put 2R. Instead of voltage, put EMF over 2 and square it. EMF squared over 4 times 1 over 2R. EMF squared over 8R. Choice D. Not too bad.
Yeah.
Okay. Question 32. Let's see what's happening in question 32. So what do you think is happening in question 32?
I don't know, I haven't read it yet.
Okay, so we have a particle of mass m, charge q, moving with speed v to the long parallel to a long word. Okay. Stop. These messages, bro. People send 4-second messages, voice messages. Send the whole thing in a minute. No, they send 4 seconds, 5 seconds, 4 seconds. What are we? What the heck? So weird. All right. So look. Force that's caused the magnetic force on a moving charge. Do you know the equation for it?
It's in the equation sheet.
Wow. QVB sine theta.
Yeah.
So now originally we had a current of I, a mass of M, a Q,
And a V.
R, and F. But now we have, oh, and the velocity was V.
Yeah.
Now the velocity got doubled. Same distance. Same current. So look, since F is equal to QVB sine theta, F is going to be direct with the velocity. And so if the velocity doubles, the force will also double. So 2F. Okay. Red light. First of all, when they say absorption, that means we have to go up. So it's not going to be D, and it's not going to be C. Either A or B, that's number one. And here it says we have red light and blue light. Which one has more energy?
Red.
Wow.
Really?
Blue has more energy.
Why?
It just is.
I need to review this topic.
Blue frequency is more than red frequency. So blue wavelength is less than red wavelength.
Yeah.
So blue light has more energy, it has more frequency, it has less wavelength. So red light has to have less energy, blue light has to have more energy. The longer the line, the more energy it is. So A is red. A student wants to determine if the resistor is ohmic. Ohmic means V is equal to IR. And if you were to plot I versus V, you should get a straight line going up.
Yep.
Or if you were to plot P versus I, you should get a parabola, because P is going to be direct with I squared in that case. So here, when the current doubles, the power has to be double squared, yani 4. When the current doubles, the power has to be 2 to the power of 4. Yani 4 times bigger. That's the case, right? That's the case. So every time the current goes up by a factor of 2, the power goes up by a factor of 4, which does mean that
It's ohmic.
it's ohmic. It's ohmic. It's not linear, but it's going to be proportional to the square of the current. State B. Okay. We know that in state A the temperature is 190. Let's look at state A. So temperature is going to be direct with pressure times volume. In A, the volume is 0.2 and the pressure is 2, which is 0.40. But in state B, the volume has become 5 times more and the pressure is the same. So we're going to have 2.00. That means the temperature had to increase by how many times? By 5 times to go from 0.40 to 2. So you're going to take that 190 times it by 5. Just question 36. So here we have the application of Kirchhoff's rule, where 1.5 ampere ends up somehow as 0.5. That's only because some of it went through the middle branch, which is the 1.0. That means the R1 has to be receiving 1.0 ampere. So going toward the bottom of the page. So the movement of a circuit inside a magnetic field, where the magnetic field is being varied, would result in what we call electromagnetic induction. Okay, electromagnetic induction. So far so good? Okay. And basically, so EMF, or the induced EMF, is equal to the change in the flux over the time. And the change in flux means the change in the field times the area over time. The area is not changing because we're still within the field, but the field is changing by itself. So essentially, EMF is going to be direct with change in the field over time. And right now, the y-axis is the field, and the x-axis is the time. So essentially, the slope is that. EMF is going to be direct with the slope. So where is the line the steepest? From 2 to 4, right? From 2 to 4, the line is going to be the steepest. Question 38. Figure 1 and 2. Okay. So by the way, the magnetic field lines have to be concentric. That means they have to leave the North Pole and they have to end up in the South Pole. And they have to be concentric circles. So figure 1 is correct, not figure 2. Yeah. Okay. They form closed loops. Exactly. 39. So look, element X has a half-life of 50 days. Y has a half-life of 100 days. So here we have 0.8 gram of X becoming 0.4 gram of X, then becoming 0.2 gram of X. How many half-lives is that?
What do you mean, like how much? It's halved by?
Why did you? We have 2 half-lives. And the half-life of element X is 50 days. So that means if we have 2 half-lives, that's going to be 2 times 50. So it took us 100 days. They're saying in those 100 days, how much of Y would remain? Well, Y has a half-life of 100, right?
Yeah.
And so if you take a 0.8 grams in one half-life, which is 100 days, it would become exactly half, which is 0.4 grams. So that's choice C. Question 40. An object is placed near a converging lens, which basically means going to be thick in the middle. Okay? Thick in the middle. You want to calculate the focal length. Well, what we know is that 1 over F is 1 over HI or SI, plus 1 over SO. We also know that HI over HO is equal to SI over SO within the absolute value. So you want to calculate the focal length, right? You must have access to SO and SI, or at least one of them. So let's see. If you have access to distance of the lens to the object, that means you have access to SO, and the height of the image, which means the HI, you would still have a missing SI, correct? But look at choice B. You have access to the SO. So now we tick that. You have access to magnification. So this whole thing is known. And of course, if you know magnification, and if you know SO, you can also find out SI. And once you know SI, you can apply this equation. And you can find...